Okay, another short one here, and this is the second factor that is baked into all of these climate models that scientists use to model the current and future behavior of the Earth's atmosphere and oceans and what we expect for changes in our climate. So the first one was albedo, now it's the last video, and this one is solar cycles. So we're going to look at two different solar cycles, and this one has to do with cycles in the output of the sun. In other words, how much energy it's outputting at any particular moment in time. We'll actually look at another so-called solar cycle, though in that case we're not looking at the sun's output so much as we're looking at how much the distance between the Earth and the sun changes. And that, as you might imagine, also changes how much radiation from the sun the Earth actually receives. But that's from the next video. For this one, we want to point out that the basic and most well understood oscillation in the sun's output is something that lasts about 11 years. So it goes through a complete cycle from a high to a low and then back up to a high in about 11 years. And this is remarkably consistent over as long as we have records for, and beyond that, using some proxy data, kind of like how we use proxy data to come up with the temperature history of the Earth. Scientists have pieced together that this 11-year cycle in the sun's output of energy is quite consistent for thousands, perhaps even millions of years. This series of pictures was taken by a sun observing satellite in the X-ray spectrum and then given false color. So if we look here, we're looking at photos sort of essentially once per year, and we're looking at one where the solar output is very high, also right here, sort of at the end of the cycle. And then as we move from picture to picture here and back around this little cycle, it's a nice little graphic, isn't it? We can see that right about here is where it reaches its minimum output. Now, admittedly, this is only in the X-ray, but this correlates with its output in all of the other parts of the electromagnetic spectrum. So, how do we identify this, and how did we identify it before we had sun-observing satellites like this Japanese satellite that created those X-ray spectrum pictures that we just looked at down here? Well, it turns out that the presence and number of sunspots correlates with increased solar output. So what we've got right here is about 400 years of sunspot observations. Now, a lot of this is actually direct observational data. Humans have been interested in the sun for hundreds of years, and for hundreds of years we've had the tools to detect maybe not a lot of detail about sunspots and where they are and how, like, not the kind of detail we have in modern day, but still pretty solid data going back a long way. And even before that, we have data where we are reasonably confident based on some proxy data and some anecdotal human observations that sunspots were of a certain number at a certain time. Now, we don't have time to talk a whole lot about all of this thing. This is a very famous minimum in the number of sunspots that is observed called the Maunder minimum. And that correlated with a period of reduced solar output, fewer sunspots, less solar output in terms of energy. And then, as you can see, there's this 11-year cycle. Look, so you look here on the axis, you've got about 50 years. And in those 50 years, you've got 1, 2, 3, 4, 5, approximately, cycles going up to the peak and back to the peak, up to the peak and back to the peak, after going to a minimum. And so this 11-year cycle repeats and repeats and repeats and repeats and repeats and repeats. And the black curve represents an average in solar output during that time. You notice that we're actually in a period of time where the average solar output is relatively high. And those people who want to poke holes in the science of climate change tend to point to this as one of their major points. It's like, well, the sun is in a historic maximum output regime, and that means that is the thing that's causing our recent run-up in temperatures, not our release of a lot of extra greenhouse gases into our atmosphere. However, the best scientific data that we have thus far is that this relatively small increase in the amount of solar output over this time really doesn't affect our temperature here on the Earth very much at all. Okay? So, for one thing, you can see here in this graph, courtesy of NASA, that the temperature record of the Earth, so that's in orange, there, goes up pretty significantly in the last 30 years or so, even while the solar output seemingly peaked somewhere right around 1950, 1960, and has been on a slow and slightly wobbly decline since then, and yet the temperature run-up has continued. So there's that. So there's not a tight correlation between solar output and the temperature that we're observing. In addition to that, when you go through all of best available science based on satellite data and direct temperature measurements and proxy data and all of the various scientific studies that have rolled into the graph that we see here at the top that well-mixed greenhouse gases, so we're talking CO2 and methane and things like that, plus ozone, plus a whole bunch of other things, all of those effects are far larger than the effect of increased solar irradiance. Okay, there it is, this tiny little bar right down there. Okay. Now there is error, that's what the error bar is here. It could be as large as this and as small as nothing. Okay. But the change in the temperature as driven by the change in the solar output over the last 50 years is tiny, dwarfed by the kind of effects that we as humankind are exerting on our climate and on our global climate as well as our regional climates. So next time we're going to talk about the other solar cycle, the one in which there is a variation in the distance between the Earth and the Sun, both on a yearly basis and also in a cyclical and much longer time period basis. And I will see you then for that discussion.